I heard you for most of that. Could you repeat it?
Hypotonic solution is when it's more water outside the cell and less solute outside the cell, right? And hypertonic is when it's more water inside the cell.
Yes. So when we have a cell, and it's usually a cell, but it can be one of those U tubes. It could be a lot of stuff. You have a cell, and you're asked, is this solution hypotonic, hypertonic, or isotonic? And the key word here is tonic, and then the prefix that you have to consider is, could someone close the door, is either hypo, hyper, or iso. Hypo means low, hyper means high, and iso means equal. Does that make sense? So far, everybody remember that? All is good? All right. So when you're talking about a hypotonic, that means that the solute is low. Hypertonic means the solute, and where? Outside the cell, is high. And iso means it's equal. The concentrations, right? We're good? That's it. So if you know that, then there are consequences to that, right? So if the solute's high inside, that means it, or low inside, outside. If the solute is low outside, what is the solute inside? High solute. If the solute is low outside, what's the water? Water's high outside. And if the solute's high inside, what's the water? Low water, right? So there are consequences to everything. And you could do that with all of it. If the solute's high outside, then the water is low outside. And by the way, I'm really impressed with how you phrased it. Your question's amazing. I wanted to say that because I was, like, initially I listened to you and I was just impressed. I'd say your name to the recording. Inside the cell, actually, I've had such a hard day, I almost feel like crying that you knew enough to ask a question like that. It's really been a long day. All right, so solute, if the solute's high outside, it's what inside? Low inside, and so therefore the water is what? High inside. So see how much information you can have just by knowing all that? But you know what's really cool about this system? Once you understand these fundamentals, you can forget. You know, there's a famous jazz artist. I think it was Thelonious Monk. Do you know Thelonious Monk? You ever listen to jazz? No, it's one of my favorite.
I like to do it when I go to sleep, and I'll be looking at the name.
Ah, okay. Well, Thelonious Monk was one of the. Look him up. He's one of the great musicians, American musicians. You know, a lot of our musicians weren't born in America. The music is one of the most fundamental American music, classic kinds of music. Of course, you don't have to like it, but just know it's very American. Thelonious Monk said, it's very hard to play good jazz. It's hard to be a good musician, right? It's a lot of practice. And Thelonious Monk said, look, music is like this. You have to practice, 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 practice. And then at some point, you set down your sheets and you just play. So when you're looking at this kind of information, you have to know all this background information, but at some point, you don't need to go back and look at all that. Just by knowing that it's hypotonic, if I tell you that something's hypotonic, then hopefully you automatically know that water is going to go where? From outside to in. So it's going to go in, and so what that means, if water's going in, then you know it's going to swell. And that's it. Just because you see hypotonic. Because now, you need to know you should understand all this, right? The solute's low outside relative to inside. There's high water, so water's going to go from out to in. You should know all that. But if you just memorize hypotonic, water goes in, boom. You know, at some point, after you do all this work, you have to know what you're talking about, and it's really easy. It should be a fast answer. Now, let's go ahead and take a look at the next one. The next one says hypertonic. Now, again, you should know everything that has to do with what we just talked about. But if it's hypertonic, what's going to happen? Water goes from in to out. Just that simple. Water goes out. That's it. Water. Now we're talking about osmosis, obviously. We're talking about water. Remember, if the solute can move, the solute's going to move, right? So
And it goes straight.
and it'll shrink. Good. See, because it's out, it's going to shrink. Now, you should be able to figure that common sense should drive your answers. Logic should drive your answer. If water leaves, it's going to shrink. If water's going in, it's going to swell. There should be a lot of logic behind this. Should be that, I hate the word, but I'm going to go ahead and use it. It should be common sense, right? Right? It makes sense. All right. Isotonic, there's no change, right? Isotonic's equal, there's no change. Equal concentrations of solute and water inside and out. You're done. Are we good? All right. Remember, osmosis only happens if the solute can't move. If the solute's going to move, the solute will move and it'll equilibrate on its own. You won't have any water moving.
So if diffusion happens, osmosis not?
In a way, I hate to say that because osmosis is a type of diffusion.
Yeah, but I mean,
If- yes.
the solute moving, the water is not going to move.
That's right. Because the solute will move to the equal out the concentrations. The water doesn't have to move. Are we good? All right. Yeah.
Isotonic, does everything just stay still or do they switch at a constant rate?
Good. Remember that. That's important. We call it dynamic equilibrium. It's dynamic, meaning it's going to be moving. Right? So you're having movement in both directions. If you have equal movement in both directions, then there's no net change. Do you agree? If you have one going out, for every one that goes out, one comes in, what's going to change? Nothing.
So it's moving the solute and the water?
It doesn't matter. Whatever you're talking about, if it's at equilibrium, they're moving in equal directions. If the solute's not moving, then they're not moving in either direction, right? If the water's moving and there's no net change, it's isotonic. It means the concentrations. Remember, isotonic actually means what? The concentrations are equal. Once the concentrations are equal, nothing's moving in one direction over the other. They're moving equally in both directions. Does that make sense? Okay. No? Someone say no? Yes? No? Okay. I thought I heard no. All right. Great question. Fantastic discussion. What else? What do we got? Anything active and passive transport?
Oh, is it active transport like when the solute needs energy to move?
That's right. That's right. So there's the book, the activity we used had kind of two examples of active and passive transport, or active transport. So there's one, the most famous, the one that everybody loves to put on tests. ACT loves it. Oh my God, crazy number of questions on the ACT on this. And the course exams love it. Pro core exams love it. Everybody loves this. Is sodium and potassium. Now, understand, sodium and potassium, the reason they love it is it's an incredibly important balance. Sodium, the balance or the concentration of sodium in your body and potassium in your body impacts your heartbeats, obviously determines your health. So you need to understand that the reason they love using it is because it's so important, that balance of sodium and potassium. Understand that people that have high blood pressure, it's because they have too much sodium in their blood, often. Not always, but often. There are other reasons, obviously. High blood pressure is a complicated, this thing is just acting up. Hold on, let me pause this. All right, so when you're talking about sodium and potassium, what happens with sodium, if the yellow is sodium, okay? What happens with sodium, let me make a little notch here, because this is the kind of thing they love to do. And make a notch over here. So they love to draw this because sodium uses uses energy, it uses ATP. In fact, this is called an ATPase pump. Sodium potassium ATPase pump is actually the full name of it. And what happens is that you get 3 sodium atoms or ions bonding to the inside of of this protein. When that happens, and you get an ATP coming in, going from ATP to ADP, the phosphate sticks here. Let me undo that. The phosphate is here, okay? When that happens, this protein changes its form. It changes what it looks like. So if I were to erase this and make this here, so it goes from this to it goes from this to this. See how it opened up? And what you're left with is the phosphate still there. And as soon as it opens up out to the outside, these sodiums kind of get released into solution. So the sodium gets kicked out of the cell. Now this sodium is actually much high. This is a high concentration of sodium outside the cell. That's why you need this ATP, because you need to push it. It needs to get pushed out. You're literally pushing the sodium out. And then inside you're left with less sodium, because this is low here, low on this side for sodium, and high on this side for sodium. So you're going from low to high. That means you need energy. You need that ATP. Once that happens, once these sodiums leave, then what happens is that potassium comes in. Let's make potassium what color? White? No, I already used white. Let's use blue.
Green.
You think green? Okay. I used green too, but let's go ahead and use green. You know what? I know I'm crazy, but I'm going to go ahead and keep this green. So let's use the white triangles as potassium. So every three sodiums that go out, you get 2 potassiums coming in. You see they go here and here. They attach. And as that happens, the protein changes shape again. We call these conformational changes. The protein changes shape again. And what you end up with is kind of these triangles stuck on here. Oh, my lack of drawing skills always ends up. I always wish I would have paid more attention in art. I know a lot of kids make fun of art, but let me tell you, I envy people that can draw well. So, as soon as you this thing, man. As soon as you see this, what happens is that this protein changes form one more time, and what you get is something that looks like you get my point, right? The potassium gets kicked out on the inside, but then so does that phosphate. The phosphate goes away too. And now it's right back to the beginning again. What's going to come in and bond here? 3 more sodiums, right? So that just keeps pumping out sodium, pumping potassium in. So that just keeps happening over and over again. That's why we call it, how do we know it's active transport? There's two things that tell you it's active transport. That's perfect, yeah. The use of ATP. As soon as you see this happening right here, it's active transport. What's the other clue that tells you that it's active transport? It's moving from low to high. But that's good, that's right. It's moving from low to high. If you see something moving from low to high, boom, it's active transport.
So with that, so does active transport always go from the cell into the outside?
No,
Okay.
you can't tell it that way. Don't do that. You have to go, like for instance, moving this potassium, you asked that question, let me show you this example, that if you're moving this potassium from outside to in, guess what the potassium is over here? The potassium is high over here. And potassium is low outside. So you see that? So absolutely not. So in this example, you have both potassium and sodium going from low to high, and you're using ATP to do it, to make that happen. Are we good? All right. So that's a really great question, a very important question, and that's active transport. Now there's secondary active transport, which is something will definitely be on the test. There it is. Sodium, potassium, ATP. I'm putting at least 2 questions on the test on that. At this point, because we're moving into photosynthesis, I think it's important that we understand how that works. We can couple transport with something else, right? So let's go ahead and show you what that looks like. So I can move things. I can have a protein over here, and this protein could be using ATP to ADP, and this protein could be taking let's talk about hydrogen ions, because that's what we're going to be talking about for next week. And this could be high over here, and this could be low over here. So we could be moving hydrogen ions this way. Do you see that? So that's obviously active transport. We're good with that, right? Well, we could do something else though. See, we can take a little bit later, a little bit further down on the same membrane, a little bit further down, and we could have, and we really usually don't do this with just hydrogen ions, but let's just go ahead and use this as an example. We could have this molecule here, this really big molecule that can't get in by itself. We'll call this molecule X, okay? So X wants to get in. Well, what we can do is, as hydrogen comes in, guess what comes in with it? So X comes in as well. So this is called co-transport. And in co-transport, what we're doing, you notice that we're not really using ATP, right? It's not really using ATP, but it is a form of active transport because what are we using? We're using the ATP a little bit earlier. And we're creating this high and low, and that drives it because this hydrogen comes in, because this is high, right? And this is low. As hydrogen comes in, naturally, it's going to bring in the X with it. So that's a form of what we call co-transport. Are we good with that? Yeah, question.
Does the hydrogen have to bond to the...
No, it doesn't bond. It just happens, it pulls it through via charge, or maybe the X bonds to the protein. But as the hydrogen just flowing through, it's almost like X is a raft on a river, and you're going over a waterfall. Do you have to put any energy in to falling over? No, but somehow the water had to get high, right? Before the water can fall, before it goes over the waterfall. So it took energy to get that water to the high in order for that water to fall. Does that make sense? All right, so it took energy to get that hydrogen over here, create that concentration gradient in order to let that X come through. So that's a form of co-transport. I may or may not put that question on the test, but you should be aware that I'll without a question. Huh?
You gotta draw that?
No, you'll have to identify it. If is it active or is it passive? I might put blank goes to ADP. What's blank? You know what I'm saying?
You gonna post this video?
Yeah.
You still have more questions, Ron?
Yeah, let it go. Let it go. Small things like that, I'm okay, but come on. Put a question mark on it. Until next time.
Okay.
Yeah, here's a pen. Are we all good with that? Any other questions about this stuff? So we got much active done, passive, there's two kinds, right? There's more two kinds, but we know there's simple diffusion, right? There's what else? Facilitated? Lord. I don't know, whoever invented this, all the work that went to making smartphones, I'm just very happy. My life is so much better. So facilitated diffusion obviously is diffusion with help, and the help comes from proteins. Transport proteins, perfect. They could be channels, they could be channel proteins, right? Or they can be proteins, carrier proteins, like we just saw. We just saw a carrier protein, but that was during active transport. Carrier proteins can also be used in passive. How do we know if they're using a protein, if it's facilitated diffusion or active transport? Is ATP being used? 1. 2, are they going from high to low or low to high? If they're going from high to low, it's diffusion, right? Okay, so that's a channel. We're good with all this? And so far, you guys can take and look at a cell and tell me if something's going in or is it coming out, right? I'm going to tell you, I'm not going to give you more than one ion. I'm not going to do that. I know that one of the practice problem sets, I gave you like multiple ions. I'm not going to give you any water potential problems, so you don't have to worry about that. Okay? I'm going to look at real simple questions. It should be an easy test day. It shouldn't take the whole day. It should be fast. Are we good? Any questions? If you studied and did the practice problems and understood the practice problems, you read the chapter, you understand the chapter, you're ready to go. I don't see a problem. We're good? All right. Have a great day and great weekend. Get some work done this weekend. Don't wait till last minute, please.